Hi, I am Sanjay Patel. In this video, we are going to learn the concept of homomorphisms of rings. A homomorphism of rings is a mapping from one ring to another ring, which preserves the operations of the rings. That is, there are two operations, as you know, in a given ring. One is called addition, other is called multiplication. So it is a function from one ring to another ring. So let me define this precisely. So definition of homomorphism of rings. So let R plus dot and R dash plus circle and dot circle be two rings. Remember that I am taking any two rings. Both are here different rings. One is with operation plus and dot, and in order to distinguish the two operations, addition and multiplication of the two rings, we are taking the different symbols. Here it is plus, that is the addition of the ring R, and this is plus circle, which is the addition of ring R dash. Similarly, dot and dot circle are the multiplication operation of R and R dash respectively. Okay, so we are given two rings, any two rings. Remember, R and R dash can be same also. So a mapping or a function, let me say a function from say R to R dash, which satisfies the following conditions. And the two conditions are, the first condition is phi of A plus B is equal to phi of A plus circle phi of B. This is true for every A and B belongs to R. And phi of A dot B is equal to phi of A dot circle phi of B for every A and B belongs to R. So if a function or a mapping from R to R dash from one ring to another ring satisfies these two conditions, then this mapping is said to be a homomorphism. Then phi is said to be a homomorphism of rings. Okay, so this is a homomorphism from R to R dash, and we say that the two rings are homomorphic. Okay. Before we take examples of homomorphisms of rings, let me explain you that what is happening in this homomorphism. Suppose we have say one ring R, another ring R dash. Okay, this is R, and this ring is R dash, and phi is a function from R to R dash. Okay, so if we take any element here in this ring, say A, its image, or you can say simple language, its value belongs to this codomain. If we take B here, its value belongs to this codomain phi of B. Okay, and the operations of this ring are plus and dot, while the operation of this ring are plus circle and dot circle. These are the two addition and multiplications of the two rings. Okay, here this plus is written between the elements A and B which are in R. So this plus is the addition of ring R. In some book you'll find that they're using the same notation for both the operations of domain and codomain. That I can explain like this. Say if I write phi of A plus B is equal to phi of A plus phi of B, then remember that these two plus are different. They are not the same addition. This plus is the operation of the ring R and this plus is the operation of the codomain ring. Same way, we can have the operation phi of A dot B is equal to phi of A dot phi of B. So in this case, this dot is the operation of R, that is multiplication in R, and this dot is the multiplication in R dash. So it is clear from the context where the addition or multiplication sign is written. So in some book you will find the same symbol is used for both the rings codomain and domain. Okay. Let us see some examples of homomorphisms. But in order to have more clarity, I will be taking as far as possible different notations for the operations of domain ring and codomain ring. So let us start with the first example here. This is the very simple one. Phi be a function from a ring R plus dot to another ring R dash plus circle dot circle. Okay, remember that R and R dash are any two rings. We don't know what are the rings, and this function be defined as phi of x is equal to 0 dash for every x belongs to the ring R. Okay, so this function or this mapping takes all the elements of the domain set to the 0 element. This 0 dash is the 0 element of codomain ring. This is the 0 element of the codomain ring R dash. Okay, then prove that this function is a homomorphism. Phi is a homomorphism from R to R dash, okay, and this homomorphism is known as the zero homomorphism. This is called zero homomorphism. Okay, the proof of the fact that this is a homomorphism is very simple. Just we need to check the two conditions. So I will be writing directly. I will start with any two elements in the domain ring that A and B belongs to R be arbitrary. Okay. Then we know that A plus B and A dot B both belong to R. What I need to prove is phi of A plus B is same as phi of A plus circle phi of B. So the first thing I am going to prove here is then phi of A plus B. Since A plus B is in the domain, its value under the function phi is 0 dash, that is 0 dash, and this I can write as 0 dash plus 0 dash because 0 dash is the 0 element of the codomain ring, and this plus I must write plus circle because we are now in this 0 dash is the element of R dash, and in R dash the operation of addition is denoted by plus circle. This I can write as phi of A and plus circle phi of B because for any x phi of x equal to 0 dash, so I can have phi of A equal to 0 dash and phi of B equal to 0 dash. So what I have proved is phi of A plus B is equal to phi of A plus circle phi of B for every A and B belongs to R. So this is my first result. Same way, we can prove the second condition that phi of A dot B, remember A dot B also belongs to R, so its value under the function phi is 0 dash. This 0 dash we can write as 0 dash into 0 dash, but this dot is the multiplication in R dash, that is in the codomain ring. So I'll be writing the symbol dot circle. Okay, so this I can write as phi of A, because for any x, phi x equal to 0 dash, so I can write phi of A is equal to 0 dash into phi of B. Okay, this is just by definition of the function phi, and this 0 dash is the zero element of R dash or the codomain ring. So what we have proved is phi of A dot B is equal to phi of A dot circle phi of B for every A and B belongs to R, and this is my second result. So from 1 and 2 it follows that phi is a homomorphism. Is a homomorphism. Okay. So very simple example, but this homomorphism is known as zero homomorphism that you can remember. Let us take another example. Second problem. Say let R plus dot be a commutative ring. With characteristic of R is equal to small p, where this p is a prime number. Okay. Then define a function or a mapping from the ring R to itself. R plus dot to R plus dot as phi of x is equal to x raised to p. X raised to p for every x in R. Here note that domain and codomain rings are same. Then prove that this phi is a homomorphism. Homomorphism. Okay. Homomorphism. Okay. Here, you know what is the meaning of characteristic of a ring? If you say characteristic of ring R is P, then P is the smallest positive integer for which P times x is equal to 0, the 0 element of the ring, for every x in the ring. So that is to be noted. And we want to verify the two conditions to show that this is a homomorphism. So let us prove. The first condition is we start with any two elements, x and y belongs to R, be arbitrary. And I start with phi of x plus y. Remember, the operation of addition is denoted by plus in the domain ring, so I am writing plus here. And for x and y belongs to R, we know x plus y and x dot y both belongs to R. Okay, and for any element in the domain, the value of the function is given by that element raised to p. So I can write this is equal to x plus y raised to p. And we know that if characteristic of a ring R is a prime number p, then we can write this as x raised to p plus y raised to p, because we have proved a result in our earlier videos that if characteristic of a ring R is p, which is prime, then x plus y raised to p is always is equal to x raised to p plus y raised to p for every x and y belongs to R. So I am using this result which I have proved earlier. Okay, and the ring R is also commutative, that is given. And phi of this x raised to p I can write as value of the function at x, and this I can write as value of the function at y. And remember, domain and codomain rings are same, so we have used the same notation in this case. The same operation of addition is there. So this is true for every x and y belongs to R. Okay. So the first condition is proved. This is condition number 1. Let me prove the condition number 2 for multiplication. Say phi of x into y is equal to, again x into y is an element of R, so I can write this as x into y raised to p, which you can write, because the ring is commutative, we can write this as xy into xy into xy p times, and then it can be written by taking groups of terms containing x and y together. We can write it as x raised to p into y raised to p, which is nothing but phi of x into phi of y. So this is again a very simple thing for every x and y belongs to R. So this proves that this phi is also a homomorphism. So therefore, phi is a homomorphism. So very nice and important example. But you are supposed to prove this this step, that yx plus y raised to p is equal to x raised to p plus y raised to p. Okay. So this proof we can write here to go from this to this step, which we have already done in our previous lectures. Let us take another example of homomorphism. Let us take the third one. Let phi be a function defined from the ring of integers z plus dot, where plus and dot are the addition of integers and multiplication of integers, to say the ring Zn, comma plus n, comma dot n of residue classes modulo n for n belongs to capital N. That is, n is some fixed natural number. So this be defined as a function from the ring of integers to the ring of residue classes modulo n, be defined as phi of say m is equal to the equivalence class of m. Okay, this is for every m belongs to z. So this is a very important example, and you want to prove that this phi is also a homomorphism, Okay, this is a very, very important example of homomorphism in abstract algebra. Okay, we are going to discuss something more about this problem later on. Let us prove this first. So I am starting with the first condition, but let me explain. For example, if we have a function phi from z plus dot to say z phi, comma plus phi, comma dot phi, defined as phi of m is equal to equivalence class of m, then we have phi of, say, for integer 3, we get equivalence class of 3. Okay, but if we have phi of say 13, for example, then this is equal to equivalence class of 13. But you know that class 13 does not belong to z phi, so we write the equivalent form of this. This 13, you know, it is equivalent to class 3, because 13 is congruent to 3 modulo phi, because 13 is congruent to 3 mod phi. So every time you have to mod out the result. So if I have the two elements like this, say if I take say class 4 and class 3 belongs to z phi, sorry, if I take 4 and 3, not class 4 and class 3, suppose if I take 4 and 3 from the domain, okay, and write phi of say 4 plus 3, that is phi of 7, and that gives me equivalence class of 7, but equivalence class of 7 is same as equivalence class of 2. And on the same way, if I find phi of 4 plus phi of 3, remember these are the values of these elements of the domain. So this plus is the addition in the codomain ring. The addition of the codomain ring is plus phi, so I must write plus phi. So if I am finding the right hand side, what I am getting here is phi of 4 is class 4 plus phi class 3, and again it is same as class 7, which is equal to class 2. So in this case, phi of 4 plus 3 is equal to phi of 4 plus phi of 3 is proved. This is just an understanding that what is the meaning of this special function phi of m is equal to equivalence class of m. Now, by the properties of addition modulo phi and multiplication modulo phi, or in general addition modulo n and multiplication modulo n, we can prove that this phi is in fact a homomorphism. So the first condition I want to prove is phi of say m plus k, for example, is equal to equivalence class of m plus k, which we can write as class A class m plus n class k by taking the modulo n operation. This is same as phi of m plus n phi of k, and this is true for every m and k belong to the domain ring, which is Z. Okay, so the first condition is proved, okay, that phi of m plus k is equal to phi of m plus n phi of k. Remember, in the domain we have set of integers as the ring and its operation is plus, addition of integers. In the codomain we have the ring Zn, whose operation of addition is plus, and that is addition modulo n. Same way, phi of m into k we can write as class m dot k, which can be separated and write as m dot n into class k. So this is same as phi of m dot n phi of k. Again, this is true for every m and k belongs to Z. So what follows here is phi is a homomorphism. Therefore, phi from the ring Z to the ring Zn is a homomorphism. A very important example. Okay, so we have done these three examples. Let me take one more very important example about homomorphism. So next, I'm going to take problem number 4. Say, let R plus dot be a ring with unity, okay, and define a mapping from the ring of integers z comma plus comma dot to this ring R plus dot. This R is an arbitrary ring with unity. So I don't know what is the set R, and I don't know what is this operation plus and dot. It is not the addition of real numbers. Remember, R is not the set of real numbers. It is the symbol for ring. We define a function phi from Z to R like this. Phi of n for any n in the domain as n times 1 for every n belongs to Z. Okay, then prove that this phi is a homomorphism. Just to understand what is the meaning of n times 1, let me take one particular case to explain this. And one more thing, that see, suppose if I take the ring R as if I take R as say Z5, okay, and the operation plus and dot is plus phi and dot phi. Dot is dot phi. Then the meaning of this, for any element in Z, suppose if I take say some number in Z, say 4, then phi of 4 means 4 times 1, and this 4 times 1, this 1 is the unity element of the codomain ring of R, which is, in our case, in this particular case, it is Z5. So this unity is actually class 1. Okay, so I can write it as 4 times class 1. This 4 is an integer, and 4 times class 1 means class 1 plus, and this plus is the operation of addition modulo phi, class 1 plus class 1, and 4 times, it is 4 times. So this is the meaning actually. So n into 1 means the unity 1 of the codomain ring is added n times. So this gives you 1 plus 1 plus 1 4 times, so it is 4. So phi of 4 is 4. Okay, but if I take say some other elements, if I take phi of say phi of 9, what I will get is 9 times 1, and 9 times 1 means 1 plus 1 plus 1, 1 plus 1 plus 1, 9 times. Okay, and that gives us equivalence class of 9, but equivalence class of 9 is same as equivalence class of say 4, because 9 is congruent to say 4 modulo phi in this ring Z5, if I take the codomain ring as Z5. Okay, so likewise you can understand how to find the value of this function. So again, let us come back. Phi is a function from the ring of integers to an arbitrary ring with unity, defined like this: phi of n is equal to n times unity 1. Okay, our aim is to prove that it is a homomorphism. So let us start with the first condition. Let any two elements in the domain, let M and N belong to the domain ring. This Z is our domain ring R. I should not use the symbol R here, because R is already used for the codomain ring. So let M and N belong to Z, that is the codomain ring, be arbitrary. Then I can find phi of M plus N as M plus N times 1. Okay, M plus N times 1. So this I can write as 1 plus 1 plus 1 M plus N times, M plus N times. Or other, instead of this, we have already proved the properties of this kind of say operations. So I can use that property directly, which I have mentioned in my earlier videos. So this I can write as M into 1 plus N into 1. I can use the distributive property. Remember, this 1 is not an integer. It is a unity element of the ring R. So let me again make it clear. This 1 is the unity element of the unknown ring R, which can be anything. If R is the ring of matrices, this unity 1 will be the identity matrix. Okay, so like that. And this gives us say phi of M plus phi of N. So what we have proved is phi of M plus N is equal to phi of M into phi of M plus phi of N. So this thing is proved. And this is true for every M and N, because M and N are arbitrary elements of the domain. So the first condition is proved. For the second condition, we take again the two elements M and N belong to Z, and consider that what is phi of m into n. Phi of m into n means mn, okay, mn times 1. Okay, we can write like this, m into n into 1. This I can write as m into n into 1. Okay, m into n into 1. Again, this is some element of the ring, say R. Let me call this element to be x. So let me keep x for this, where x is equal to n times 1, and this belongs to the codomain ring. 1 plus 1 plus 1 n times, it is an element of R. So I will get this is equal to m into x. Okay, this x I can write as x in 1 into x. X is an element of R and 1 is a unity element, so 1 into x is equal to x. Now this I can again rewrite as m into 1 into x, like this, because we have this result m times a into b, where a and b are elements of the ring and m is integer. I can write as m into a into b. Okay, so we are using such properties from our earlier lectures. So this is equal to m into 1 into x is n into 1, because x is equal to n times 1, and this is nothing but phi of m, and this is phi of n. So we have proved that phi of m into n is equal to phi m into phi n. So phi of m into n is equal to phi of m into phi of n for every m and n belongs to z. So this is our second result. From 1 and 2, it follows that this phi is a homomorphism. Is a homomorphism. Okay. So this way we can discuss the examples of homomorphism, and at the end of this lecture, let me give you some 1 or 2 more problems for practice. So we have done 4 problems on homomorphism, and these last 2 problems are very, very important. So you must remember this. So let me take this one, number 5, that let phi from C plus dot, where C is the set of complex numbers, to C plus dot. I am taking the same ring here, ring of complex numbers with respect to addition and multiplication of complex numbers. This phi be defined as phi of z is equal to z bar, where z is the complex number and z bar is the conjugate of z. You know, if z is equal to a plus ib, its conjugate z bar is defined as a minus ib. Then prove that this phi is a homomorphism. Same way, let me take another example. Let R be the ring defined like this. It is a ring of matrices of the form AB minus BA that are all 2 cross 2 matrices of this form, where A and B are any real numbers. Okay, this be a ring with respect to matrix addition and multiplication. So I'm writing in short form. So R plus dot is a ring. Okay, so that is R plus dot is a ring of matrices of this form, and plus and dot are the addition and multiplication of matrices. Then I define a function phi from C, or rather let me write this way, define a function phi from C comma plus comma dot, that is set of complex numbers. Set of complex numbers means ring of complex numbers to this ring R plus dot. We define this function phi in a natural way, because if you take any element from the complex number set which is of the form a plus ib, then its value is defined as ab minus ba, this matrix. Okay, this is for every complex number z is equal to a plus ib belongs to C. Then you can again prove very easily that phi is a homomorphism. Homomorphism. Okay. So these are the various examples, but out of these examples, remember that this one, yes, this phi of n is equal to n into 1, where phi is a function from z to r. And problem number 3, this is also very, very important. Okay, we are going to discuss something more about this homomorphism later on. So this is the introduction to homomorphism of rings. So homomorphism is nothing but a function from one ring to another ring which preserves the operations of the two rings. Okay, so we'll see some properties of homomorphisms in our next lecture. Till then, goodbye and thank you.